All right, good morning, everybody. Today we are going to review for our test on Tuesday. We're going to break this down into 4 parts. First part is going to be Chapter 7. Everything we did before spring break landed us with Chapter 7. So what we started with is the anatomy of a chemical equation. Basically, what are the parts? We had the reactants, and they were added together, and they yielded products. We'll take that into one big step. The next thing we did, once we saw what the chemical equation looked like, we began to balance it because we realized a few things, that we can't have parts over here that don't equal parts over there. We can't lose or gain anything. It has to be in balance. So we'll take a closer look at that as well. After that, once we know what an equation looks like, once we understand how to balance it, the next step was the molar mass calculations. Now, this takes the compound of, say, water, and it calculates, if I have a mole of water, what is that really telling me? Because a scale doesn't tell me amount. That's what a mole does. It counts amounts. I want to know how much mass that is. So how much mass is 1 mole of water? So we'll take a closer look at that as well. And then finally, we talked about the 5 reaction types. These are the 5 identifiers that tell you what a chemical reaction looks like. And it can tell you a lot about what it can do if you understand what it looks like and recognize the form. So, of Chapter 7, these are the main topics that we're going to discuss in our first half of our review. And to start with, we're going to break down these 2 components. What does a chemical reaction look like, and how do we balance it? Okay, so the very first thing we're going to look at is the anatomy of a chemical reaction. So what we have over here is iron, the metal, is going to be added to oxygen gas. Now, right off the bat, what we have here on this side of the equation are the reactants. They're the things that are going to react together. They're the things that are going to combine, in this case, to make something new, a new compound, something that's chemically changing itself from the original. Iron is iron and oxygen is oxygen. But when they combine together, they make what you and I both know as rust. Now, this is an old rusty ruler that got left a little too long outside of the house. It got rained on, and therefore it rusts. So that's what happens when the oxygen in the air combines with the iron in this steel. It combines to make rust. So the chemical equation is behind me. Now, these 2 reactants, the left side of the equation, are going to yield something. This middle marker here is called the yield sign. We've talked about it before. No, this does not mean slow down. It means how much does it produce? How much did it yield? And so what it makes is the product. You can think about it like an assembly line. If you've got a widget factory and you're trying to make widgets, well, you might need screws and bolts to make a widget. And in this case, we have reactants yielding products. And the product is what you're looking for. So in this case, over here, we have products. This is the basic anatomy of a chemical reaction. Now that we understand the basics of what a chemical reaction looks like, the anatomy of it, let's take a closer look as to how to balance it. But more importantly, why do we balance it at all? Well, think about it. The law of conservation of matter and mass says that we cannot create nor destroy anything in the universe. You can't bring anything into the universe that wasn't already here, and you can't destroy it completely by throwing it out of the universe either. And if we look at what this equation is really saying, it's saying that 1 atom of iron is binding with 2 atoms of oxygen. It's 1 plus 2. But it's saying that it's making 2 atoms of iron, that's 1 more magically created, and 1 more, 3 total, 1 more than what we started with oxygen. So all of a sudden there's 2 new atoms over here, 1 of oxygen, 1 of iron. They didn't just magically appear. So what we've got to do is we've got to balance this equation. And what we're really saying is this ingredient, iron, plus this ingredient, oxygen, will make rust. Okay? This is iron 3 oxide. It will make rust. But what proportions do they come together to make that rust? That's what we're looking for. So when we balance a chemical equation, we're saying how much of this reactant plus how much of this reactant will make how much of this product. So what we do to balance it, as you know, is we're going to place coefficients in front of that. Now, these lines represent the numbers of those elements or compound that we're going to add together. So the best way to start to balance an equation is to look at both sides as unbalanced, and I start by drawing a line at the yield sign here, and then just list what you have. You have iron, and we have oxygen. On this side we have iron, and we have oxygen. Now I just want to count how many of them I have. I know I have 1 iron, and I know I have 2 oxygens here. On the product side, we have 2 iron atoms and 3 oxygen atoms. So now all we've got to do is change these coefficients until it's balanced. Now here's something that I saw early on when you were first starting to learn how to do this. They have to be whole numbers. They cannot be parts of a number. What I mean by that is this coefficient can be 1 or 2 or 3, so on and so forth. It cannot be 1.5 or 2.6. It has to be a whole number. So make sure you remember that, because what you're really saying is you're adding 1 part of this or 2 parts of this. So we can't do the in-betweens. It's whole numbers, and that's the way it works. So let's start over here. We notice we have 1 atom of iron and 2 atoms of iron. I want to try to balance this. So what I can do over here is say, instead of to get this up to a 2, we can simply place a 2 for our coefficient. Now what that does for us here is it says now we have 2 iron atoms. Great. All right. Here's where we're going to run into a problem. This says 3 oxygen atoms. All right. Well, there's no whole number that I can multiply that 2 by to get to a 3. We have 1 right here because there's 1 O2 molecule. That's why there are 2 atoms of it. I can change that 1, which is really 1 times 2 is 2, to a 2, and that will get me to, that's right, 4. 2 oxygen atoms. What this 2 is really saying is that there's O2, O2. There are 2 of those molecules. That's what it's really saying. So that you understand really what those coefficients are meaning, that's what it's really saying. That's how I have 4 oxygen atoms on this side now. All right? Now that you got that idea in your head, we have 2 and 4, 2 and 3. This one's low now. Oh, but there's going to be a problem here. If I change this, it changes everything. That's okay. We need to balance the equation. And a lot of times you're going to see it swing back and forth like a pendulum until you find equilibrium. So this is a 3, and this coefficient is a 1. Let's see what happens if we make it a 2. 2 of these compounds. So if I make this a 2 here, remember what it's saying is I have 2 of everything in the box. I have 2 Fe2O3s. So it's kind of like in math. When you distribute it, you take the 2 and you multiply by 2. Changes this to a 4. You take the 2 and you multiply it by 3. Changes this to a 6. All right? So what we've got here is 4 iron atoms and 6 oxygen atoms. over here we can start to fix that. Let's start with iron. It's an easy fix because there's only one iron atom. This 2 coefficient, I'm going to change to a 4. And now I have 4 irons. All I've got to do is find a way, a number, a coefficient that will fix my oxygens. I have 2 of them. If I change this 2 to a 3, I now have 3 times 2, 6 oxygen atoms. This problem is completely in balance now. The coefficients to balance it with are 4, 3, and 2. So now what we've gone through is the first half of chapter 7. You've seen how the anatomy of a chemical reaction looks, and now you've seen how to balance one. And more importantly, why we do it in the first place. What this does is give you the ratios for how much iron plus how much oxygen will make how much rust. That becomes really important much later on in chemistry, but this is a firm foundation that I want you to understand before you go on to biology, before you go on to chemistry again in your sophomore year. So make sure you're really leaning into this and understanding it, not just for what we're doing, but why we're doing it. That's at the heart of all of this. Make sure you understand why we're doing it in the first place. And what we're doing is understanding the ratio of this. So the next step in chapter 7 was how to calculate the molar mass. Let's start with the product that we just created. We talked about iron 3 oxide here. What I want to know for this rust, essentially, is if I go into the lab and I put it on the scale, how much rust equals 1 mole, all right? So if we're going to talk about molar, let's remind ourselves what a mole is. A mole is an amount and an amount of a specific number. If I say dozen, you conjure up the number 12. But what a mole is for a chemist is a very, very large number. We call it Avogadro's number. That number is 6.023 times 10 to the 23rd. It's unitless, just like dozen or 12 is unitless, because you can have 12 donuts, you can have 12 eggs, you can have 12 tires. But at the end of the day, a mole is the same thing. I can have a mole of iron. I can have a mole of oxygen. I can have a mole of rust. So what we're looking at here is if I have 1 mole of this, what does it weigh? What is that in grams? Because I have a scale that can measure grams. I don't have a scale that can measure moles, and moles are amounts. So if you go and look at those dozen eggs, the best way to understand how many eggs you have is count them, but to better understand how much you have of it is to measure it as far as grams. How much does it weigh? All right? And so then you can start to compare it to other types of eggs. So if we're looking at rust, in this case, I want to know how many grams 1 mole of it weighs. So let's get started in making that calculation. Now make sure to follow along with me in your notes. Have your periodic table out right now because it's going to help you. And we're going to calculate what Fe2O3 is in grams if I give you 1 mole of it. So if we're going to be looking at this and understanding how to calculate the molar mass, you look to your periodic table and you look up the 2 elements that make up this compound. Number 1 is iron. On your periodic table, iron is number 26, and it is 55.8 for its atomic mass. But remember, this atomic mass is how many grams per mole iron is. So 55.8 grams of iron is 1 mole of iron. I'm going to round this to whole numbers so we can make it a little bit easier for ourselves. 55.8, I'm going to round up to 56. That's grams per mole. That's for iron. And now down here we've got oxygen. It's number 8 on the periodic table. Oxygen has a atomic mass of 15.99, which I'm going to round up for simplicity to 16 grams per mole. So if I had 16 grams of oxygen, I would have 1 mole of oxygen. And that makes sense because oxygen is so much lighter on the periodic table than iron is. All right? So a mole of iron weighs a lot more than a mole of oxygen. But I don't want to know about them individually. That's easy enough to look up directly. I want to know what a mole of this weighs. So here's what we use this information for. You have your periodic table out in front of you to help you solve for the molar mass of rust. I start off with iron. I know that there are 2 atoms of iron, so I'm going to say 2 atoms of iron times its molar mass, 56. Then I'm going to take oxygen. Oxygen, there are 3 atoms of it. So I'm going to say that oxygen is 3 atoms of it, but times the molar mass of it, which is 16 grams per mole. What I'm going to do now is simply add these up. I have the 2 atoms of iron, the 3 atoms of oxygen, multiplying each by their molar mass to give us an answer. Once you've taken that and plugged it into your calculator, again, I would use parentheses. So I type parentheses 2 times 56, close parentheses, plus parentheses 3 times 16, close parentheses. You're going to get 160 grams per mole. So 1 mole of rust on the scale is 160 grams on the scale of rust. Now, I put the parentheses around it in your calculator. A couple of reasons why. This wouldn't necessarily make the mistake if you forgot the parentheses. However, order of operations is important, and your calculator doesn't always understand what you're telling it unless you specifically tell it what to do. Remember, it's a machine. It only does what you say to do. So tell it to do it the right way and put parentheses around those to make sure that you don't stumble into an error just from typing it into your calculator. Now on to the last section that we learned about in Chapter 7, reaction types. There are 5 of them. We're going to start with the first type. This is a synthesis otherwise known as a combination reaction. You are taking 2 or more reactants, combining them together, hence the plus, to make only one thing on the product side. So, if you're looking at this, what I like to call the pattern formation, what you're seeing is an A plus B is going to make a B. This is the format for a synthesis, otherwise known as a combination reaction. The form is always going to be the same. Now you could have A plus B plus C, and that would yield ABC. Regardless of the nature, you have several things coming together to make one thing. That is the combination reaction. Now here, we've reversed it. We're taking water and we are tearing it apart. We're taking one thing and breaking it down into more than one thing. In this case, it is decomposing. It is breaking apart. This type of reaction is a decomposition reaction. A decomposition, to decompose, is to break down, and that's what's happening here. We have one thing, it's breaking down into multiple things. So in reverse of a synthesis, what we've got is an AB is yielding A plus B. This is a decomposition reaction. Third reaction type. What we're looking at here is two things still making two things. But the key difference here is that one of these things is going to replace itself with the other. So in this case, the two metals, the two cations, the positively charged ions, are switching places. The oxygen just gets a new partner to dance with. So in this case, iron gets booted and magnesium changes places with it. This is called a single replacement reaction. And as you can see, the magnesium now is bonded with the oxygen on this side, and the iron has been booted out. For time's sake, I haven't balanced the equation, but what I would suggest for you to try to do at home, since this is a review, is to try to balance this equation on your own, and let me know if you get it. So, this one might seem a little tricky. It's an easy spot though. What you're looking at here is two ionic compounds, and the metals, the cations, the zinc and the potassium, are switching places. So in this case, these two compounds, not a compound and an element, rather in our single replacement reaction, the two compounds here, these two metals are switching places. So the potassium will bond with the chlorine, as you see right here, and the zinc will bond with the hydroxide, as you see over here. Because the two compounds have two different metals switching, we call it a double replacement reaction. This is a double replacement. You can tell again because the two cations and the two compounds switch with one another. Again, I have left this unbalanced so that you can try to balance it at home to get some more practice. Go ahead and give it a shot. All right, we're on to our fifth and final reaction type to review. And in this case, it's an easy spot. In my opinion, as I stated in the video before, this is the easiest one to spot because you're always going to have the same products being formed. In this case, we have a combustion reaction. That's right, kablooey. In this case, we've got butane gas igniting with oxygen to form carbon dioxide and water, and that's it. So whenever you recognize a hydrocarbon plus an oxygen gas, and it's always going to produce the same two things, carbon dioxide and water, it's a combustion reaction. And a combustion reaction is always going to look the same. So when you see the products as carbon dioxide and water, you can bet your bottom dollar it came from some kind of hydrocarbon bonding with oxygen gas. We simply call that a combustion. And again, these are probably the more problematic ones to balance. I've left it unchecked for you to go through and try it yourself. Give it a shot. So we're done with the chapter 7 stuff. Let's move over to chapter 8. Now we're going to be talking about solutions, molarity, and acids, bases, and pH. What does all this have to do? If we summarize chapter 8 up into these three categories, what it's really trying to tell us is if I have a solution of something, that solution was made with two things. Let's just take something simple like sugar water. The more sugar you put in the water, the sweeter it gets. And if you don't add any more water to it, if you just have a cup of water and you put a tablespoon of sugar and then another tablespoon of sugar and then 3 tablespoons of sugar, all you're doing is increasing how much sugar there is in all of that water. And the whole combination of it, assuming the sugar is completely dissolved, is sugar water. So that's what a solution really is. It's mixing these two things together to dissolve. You need something that will dissolve, what we're going to call in a second the solute, something that breaks down, and then the other thing that breaks it down. In this case, the solvent. So the sugar in this case would be your solute, the water is your solvent, and the solution is going to be what's made, the sugar water. From there, we need to understand how concentrate is that? Is it really sweet, or is it, I can barely taste the sugar in it? That's going to depend on its molarity. Molarity is chemistry's fancy word for concentration. How concentrate is that solution? And so from there, we start to apply it to things like acids and bases. As you've seen in the last two videos, what I'm talking about here is how concentrate is that acid. So if you take the acidity of, say, a lime, that lime, it has a pH that tells us it's an acid because it's less than 7, but that acid, if I got that on my skin, lime on my skin isn't going to hurt my skin. That lime juice I won't even be affected by it. Even though it's acidic, it won't affect me. However, if I take the sulfuric acid that's found inside car batteries, and in car battery acid, that's a liquid acid, that will burn through my skin. That is a very bad acid. So its concentration is much higher acidic-wise than what, say, lime juice is. But all that has to do with is what makes an acid an acid. And we talked about that, the hydrogen ions. So we're going to briefly go through some of these. I'll work a problem here. We'll work some things out to make sure you understand how to calculate what a solution is, what the molarity is, and what an acid base and the pH scale is in review, so that you're ready to go on to some of the worksheets that I've got for you on the other side of this video. Let's get started with understanding solutions. So starting off with solutions, remember that a solution is nothing more than two things added together. So let's say I've got salt, and I pour it into a glass of water. Now, as the salt sprinkles into the water, we would get, assuming that we can break it all down, of course, and that it dissolves completely, salt water in our solution. All those salt particles would be dissolved into the water, making it salt water. And you could tell immediately that it was salt water if you went to taste it, versus the water before the salt was introduced. It's very obvious. But what were these things? Okay, well, the salt broke down inside the water. The salt in this case is your solute. A solute is anything that is chemically broken down by something, and that something in this case is the water. The water is the solvent. The solvent breaks down the solute, all right? So the solute added to the solvent breaks everything down into the solution. So there's our formula right there. The solution is equal to the solute plus the solvent. And so we can simply write that down, if you've got this. The solution is equal to the solute plus the solvent. And in this case, remember, the water and the salt were added together to make salt water. And that's all that you need to get from this. It's simply understanding how things break down. So whenever you put something and shake it up, if it's a powdered Gatorade into a water bottle, the powdered Gatorade becomes the solute, and the water is still the solvent. Water is a great natural solvent for lots of things. That's why we use it so much. And over here, in this case, it would be the Gatorade water, or the Gatorade, whatever you want to call it. In this case, we made salt plus water, made salt water. That's how a solution is calculated. Now we're going to step up to molarity. Remember, molarity is just a fancy word for concentration. And remember, concentration is how much of that salt you put into the water, or how much of that Gatorade packet you put into the water. So there is a formula for it. Now, the symbol for molarity is capital M. All right, we've used M a lot for the beginning of moles, M-O-L-S. You've used M for meters. Now we're using capital letter M for molarity. So that's going to be the unit we mark as the molar concentration, is what it's actually formalized as. But the molarity, how concentrate is that? Well, it depends on this. How many moles of solute, and think about salt water, right? What is the amount of salt water what is the amount of salt you put in to make the salt water? The liters of solution, not solvent, solution. This is how much stuff went into the solution. So in our analogy earlier, how much salt went in to make salt water? So how salty is that salt water? That's what this is saying. How sugary is that Gatorade or Kool-Aid or whatever you're drinking? So in this case, whatever you mixed together, the final product, how much of the initial thing that broke down, how much of the solute went in to make that solution? And that's what we're looking at here. That's all molarity is. And so you calculate with that. Now, in this case, it's moles, not grams. We're going to work an example of this. This is moles of solute versus liters of solution. So let's look at it in two ways. We'll stick with salt for a second, all right? And so we're going to need to know a few things. If you've got your periodic table handy, you know that salt, we'll say salt, NaCl, all right? If you're looking at both of these, we're going to need to know a few things about this. In this case, it's molar mass. In case I give you grams, you would need to convert grams to moles so that you can put it into liters. All right? Let's try that real quick. I'll put it on the board nice and clean, and we'll start with salt in salt water. What's the molarity? Okay, let's take that same example of salt water. Let's start with the fact that maybe I give you 4 moles of salt, and I give you 2 liters of salt water. First, I'm just going to make sure that I understand that all I did over here is look to your periodic table, and I calculated sodium and chlorine molar mass. So sodium is 22.99. I rounded it to 23 to make it easier. Chlorine is 35.5. I just left it at that. And we get to 58.5 grams per mole. But here's the cool thing. In this first example, the simplicity of this is that I give you moles and I give you liters. So we don't need the molar mass for this, because remember, the formula for molarity is moles of solute over liters of solution. I have the liters of solution, I have the moles of the solute. All I've got to do is divide it, and now I've got 4 over 2. Of course, that breaks down to give us a 2 molar concentration. That one's not that tough. But what if I did not give you moles? What if I give you grams? And if that's the case, we need to convert grams to moles. So I want to make sure you understand how to do that moving forward. I'm going to show you a neat little trick. Here we go. Okay, let's change the game. I still give you 2 liters of salt water. That hasn't changed. But in this case, what if I change it to 117 grams of salt? I don't want grams. I want moles. So in this case, that's when you need the molar mass, because this has grams and moles in the unit, which allow us to convert between grams and moles. So if I'm given 117 grams of salt, I want to convert it over here to moles of salt. How do I do that? Well, here's a neat little trick I'm going to put over here in the corner for you. Write this down for sure. It's a great tip. If you have grams of a substance, let's say we'll call this our gram box, and over here we have our mole box. Is that in frame? Yes, it is. If I want to go from grams to moles, all right, like what we're doing here, what I'm going to do is divide by the molar mass. That's right. We're going to be dividing by the molar mass. And here's our molar mass of whatever it is we're looking for. If for some reason later on you need to go back again, you multiply. This little picture, this is by the molar mass, of course, divide by the molar mass, of course, will give you a conversion. So for example, if I come over here and I am going to divide by 1 mole of salt, Na, capital Cl, there we go. Its molar mass is 58.5 grams. The nice thing here is our grams cancel, that's why we're dividing. And 117 divided by 58.5 is going to be, hope you wrote this down, if not rewind the video. What we get as a final answer here is 2 moles of salt. So now we take our answer here, we plug it back in. So in this case, I've got from 117 grams of salt that we started with, it's really only 2 moles of salt. I divide that, of course, and since I've cut my cut this in half from the first 4 moles, I now have 2 over 2, which is 1 molarity. So this number remained the same. I wanted to show you 2 variations of the same problem. Essentially, in this case, we had to convert 117 grams to 2 moles. In the initial case, I gave you 4 moles. You simply plug it into the equation to get your concentration. And that's it. One more thing to go: acids, bases, pH. Let's get started. So let's focus in on what an acid and a base actually is. What we're really talking about at the heart of all of this is water. Water has 2 hydrogens and 1 oxygen. Let's take a focused look. You've got H2O. If I break that apart, I really have HOH. That's the key right here. As you saw in the video, as I explained what an acid and a base was, what I'm really doing is to define an acid. This hydrogen breaks apart from the water molecule and it goes over here. To do that, it leaves its electron behind. So you've got a hydrogen atom, which is nothing more than just a proton and an electron going around it. And that electron gets taken away, you've just got a proton. So this becomes a hydrogen ion, which is nothing more than a proton. Okay? And that proton wants to go to something. So an acid is considered a proton donor. Anytime you have an excess, a large amount of hydrogen ions in a solution, high concentration, you've got an acid on your hands. On the flip side, we step over and we look at what this is. This, with that extra electron, becomes negatively charged. This again was positively charged. This is hydroxide, OH, negative. Now, hydroxide is a base. It's a pure base. But what it really is understanding here is that it desperately wants that proton back. It wants to take it back in to make water, to make it back to where it started. So what we call this is a proton acceptor. It's not missing one, it is missing one, and it wants it back. So it's going to accept it back. So a proton acceptor is considered a base. And anything basic is missing those positive hydrogen ions, whereas anything acidic is chock full of all those hydrogen ions. So essentially, what we've got here is the definition of an acid and a base. Now, what we really want to understand is how these two things come together to define the pH scale. Well, we rest right here in the middle. Before they broke apart, they were water. And even so, after they come back together, when this hydrogen ion is donated back to this accepting hydroxide, when they come back together, they come back and meet neutrally. Neutrally as in 7 on the pH scale. Little p, big H. Now, a 7 on the pH scale is considered neutral. For that reason, it's in balance. It's right in the middle between an acid and a base. It's water. It's what we define it as. But if I take that water and I add more of these hydroxide ions, then it's going to become more and more acidic. And in fact, anything between 0 and 6.9, right before 7, is considered an acid. Low numbers on the pH scale lower than 7 are all acidic. Now, if we take that and we look at how many hydroxide ions there are, anything above 7, from 7.1 all the way to 14, that becomes your base. And what we're looking at is a perfect scale of how to define an acid or a base. Now, we call this the pH scale. Remember, little p, big H. That big H is talking about the hydrogen ionizations. It's interesting. It's the concentration of hydrogen ions. Now, think about it. I gave you a list of things to do for homework. Common household items to look up and see whether they were acidic or basic, and where they fit on the pH scale. You could look at Coca-Cola and say, woo, that's pretty acidic. Or you could look at window cleaner and say, wow, that's really basic. But you can also think about the concentrations of them. So again, the concentrations of them will increase how acidic it is versus how basic it is. And where do we rate that? Right here on the pH scale. So, there you have it. Everything that we need to know from chapter 7 to chapter 8, and if you have your textbook, all of this information can be found within it. There's some good review questions inside your textbook that you can go to and check. Now, when you get to the questions for homework today, what I'm going to be asking you to do is just a few questions on each of them, similarly to what you did Tuesday. However, I will be posting several other worksheets that will not be required for homework, but will have keys, in which case you can check your answers to see if you're on the right track to solving these types of problems. But the key to all of this, honestly, is to make sure that you understand the information that we've just summarized in this review session. Because if you do, then you are well prepared to move on into the next level of biology, and more importantly, the introductory level of chemistry, which you will be seeing your sophomore year. And as well prepared as you could be now for this, the information that we've introduced you to here today will make sure that you are more than prepared to understand those lessons as they become more complex and more detailed as they move through that material in your sophomore year. I want to remind you that this is all about solving problems. Make sure that you take the time to understand the why and not just the how. I don't want you to just understand how to do these. I want you to understand why you're doing this. And you don't need to be a chemist to understand this type of chemistry. It's straightforward as long as you're using your mind. I want to leave you with that, and I'm going to leave you with this. Always remember to love the ones around you and know that you're loved.